absolute most time on. Oh, it's going to log me out, log me back in. Because this is most likely the first class that you have that goes into great detail behind enzymes, other than saying what an enzyme is. What is an enzyme? If you're going to describe an enzyme in just a couple of words or a sentence, what would you call it? Catalyst. What kind of catalyst? Like usually, like the Miss American answer that I usually get is it's a biological catalyst, right? You know, so and that is true, but you don't ever even go into very much detail about how they work and stuff. And so usually in biochemistry, we would spend, I'd say, at least 2 full weeks, if not more than 2 full weeks, worth of lectures and semesters of doing this kind of stuff because it is so important, and almost all of next semester is on enzymes and metabolic pathways. And so, unfortunately, we are much limited, so how much detail we need to go into. So we go a little faster than what we did in the past. But so an enzyme is a biological catalyst. What are they? What kind of biomolecule are the enzymes? Are they lipids, carbohydrates, proteins, nucleic acids? Proteins. The proteins, are they all proteins? I have some conviction here. Don't be afraid. No, that is correct. They are not all proteins. The vast majority, most likely, are proteins, but are proteinaceous, but they are not all proteins. Does anyone know what's an example of an enzyme that is not a protein? Or just not just a protein, I should say. What is the textbook example that's usually used? What other biomolecule can have enzymatic activity? When we say enzymatic activity, that means it can do chemistry on its own. So you want to know, think about it. I mean, without it, you would die. Biochemistry too, we die a lot. That's why I like to say. You can be fatalistic, or you can be, God has created wonderful things, so therefore, it's just more fun to say die. But that's RNA in particular. Okay. So, and the textbook example is the ribosome. The ribosome, the chemistry is actually done by RNAs. It's not just done by RNA, but it's not just RNAs. It's called a ribonucleic protein complex. I'll talk a little bit about that later on. And it's not the only one. Okay. So this is a little spiel. I apologize. Somehow, whenever it went updated from one version of PowerPoint to another version of PowerPoint, the background and the fonts didn't go along with each other. It's like blue on blue or whatever. Sometimes it can be a little hard to see. All right. So being an enzymology is my background, and being an enzymologist, I really hate this part right here. Self-splicing RNAs technically are not enzymes in the strictest sense. Okay? Does anyone know why? I almost get bonus points right now if you can explain why a self-splicing RNA technically is not an enzyme. It's acting on itself. Oh, that is right. It's acting because the enzyme, the catalyst remains unchanged, right? You can have in the beginning to the very end, it's gonna be different. A self-splicing RNA is acting on itself, so it is its own substrate. We'll talk about that in this moment. But therefore, it is changed. And so even people in enzymology, we call those ribozymes, but they are not considered true enzymes because they are their own substrates. They are changed. That's what most textbooks in biochemistry, in introductory biochemistry, will talk about that. Being an enzyme, and then RNP stands for ribonucleoprotein complexes, and that's where the quaternary structure contains both proteins and nucleic acids. And it's where the RNA does the chemistry. And so the big textbook examples are ribosome. Another one's ribonuclease P, which is what I work on. And it's really special one of these days. Maybe I'll have to talk about it because it's very different than anything else. Quite like it. Does anyone know what pathway is involved in? It's ubiquitous. All organisms have it. between mitochondria and chloroplasts. In there? No, it's a bit. It's not in your page. It was a good guess. It has to do with tRNA maturation. Okay. And so what it is, and the reason why this little brief spiel on it, evolutionary biologists love it because they usually, in fact, they've got the person, it's actually technically 2 people who discovered RNA-seq, but a couple years ago, it was on the list, a year or 2 back, actually won the Nobel Prize in chemistry. Evolutionary biologists love it because they say that it shows the RNA world hypothesis. I'm going to use it as an example. Take it for what it is. The idea is in bacteria, RNA-seq has one RNA, it's big, relatively big RNA, and a little tiny piece of protein, and at least in vitro, you take that protein away and the RNA will still work. The RNA is truly catalytic. The protein actually just helps it differentiate between substrate and product. So it's a 1-to-1. Whereas whenever you get to the humans, say for example, humans and yeast, then our RNA-seq complex, actually I don't know how many we now discovered for humans, but back whenever I was working on it, for example, yeast had 1 RNA, it still did the chemistry, and 9 proteins, and all 10 components had to be together for it to work. If you took off the other proteins, it didn't work anymore. So it showed that the RNA alone, it did the chemistry step, but it still couldn't, they said it had evolved. And then on the other end was mitochondria and chloroplasts, which evolutionarily people believe, you know, are via endosymbiosis. Those typically, those lo and behold are protein only. Okay, there's a protein enzyme. So it says, oh look, it's gone from an RNA for the ancient bacteria all the way to proteins. That's why it's a little different. I worked on it in the sense that we were comparing, my part was comparing the eukaryotic and the prokaryotic and looking at its mechanism. The idea is if we come up with an inhibitor that affects the prokaryotic, not the eukaryotic, then we have a broad-based antibiotic. Okay, but in general, enzymes can increase the rate of reaction a lot, okay? Lots and lots and lots. Some enzymes are very, very specific, but they will take not only do they only do one reaction, but they will do only one enantiomer of that reaction, whereas some of them will do lots of different things. Does anyone know, for those who have me in further classes, what is the term that they like to use in enzymology and biochemistry for that matter, whenever it's not so picky and it utilizes lots of different substrates? What's the term that gets used? They say it's promiscuous. It gets around, or they'll talk about the relative promiscuity. That doesn't mean that, and that's not, that's the opposite. Something very strict. And then we'll talk a little bit about the rate of the reaction. This is definitely an oversimplification. But the rate of the reaction depends on the activation energy in terms of free energy here. And the enzyme does it, one thing, this is so important, and we're going to prove this later on, enzymes do not affect the equilibrium constant at all. And so it's almost a trick question, but in reality it's not a trick question. If I asked you, does the enzyme catalyze which does it catalyze more, the forward direction or the backward direction of the reaction? Which one does it catalyze more? Does anyone know? Neither. It catalyzes in the same amount. Okay, and so therefore that's why it doesn't, and we'll show examples of what that does in just a little bit. Okay, some other terms. One term that actually is not on here, but I've already used, and that's substrate. Substrate it means reactant. Okay, reactant and substrate are hand in hand. There are 2 other terms. Many times myself will use, people will use them interchangeably. There's a slight nuance that's different, but even I, a lot of times, will use them interchangeably. And those 2 terms are cofactors and coenzymes. Okay. And coenzymes coming up in another slide in just a moment. But a cofactor is a small additional chemical component that's required for activity, for complete activity. Usually we're talking about, many times talking about metal ions. Those are the simplest. But it can also be a very small organic compound. Like someone would say, oh, maybe BPG, that's a small organic compound, if that's something that is required for, which hemoglobin is not an enzyme, but just as an example. It's not like there's a cutoff point that say at 2,000 grams per mole, it's no longer a coenzyme, or no, cofactors are coenzyme. They almost, for most things, when we're talking about it, we're talking about metal ions or anions, like chloride. That's the one that sometimes can be. A lot of times it's something that's inorganic. And so this is just some examples. And many of these you already know, probably hit the fun of. And so don't memorize this table. This is just showing you as we go along, especially next semester, and most, if not all of these, we will cover next semester. Actually, carbonic anhydrase we've already talked about this semester with the board effect. Yeah, many of these, if not all of them, we will cover next semester. So yeah, this is just to show you. Whereas a coenzyme, typically it's something that's a more complex organic, or this looks weird. Metallo-organic molecule. So, for example, the RNase P, I think I even used the term already. It has a big RNA that does that for bacteria. It's got a big RNA component that does the chemistry, and it's got this little tiny protein. Like I won't say, I may get the numbers a little off, but the RNA for Bacillus is like right around 100 kilodaltons. It's something really huge. But the protein's only 14, like 12 to 14 kilodaltons, so it's much smaller. And it is a metalloenzyme, that one is, so where it has a Z is important. But it just means that it goes along to make it catalytically efficient. A lot of these are related to your vitamins. So a lot of times, you can almost think of many of your minerals. There are examples, I'm sure there are exceptions. Many of your minerals are cofactors, but many of your vitamins are coenzymes. But there are other coenzymes. Some of them are really easy because it's in their name, like coenzyme A. Okay. So here's the, once again, you don't, oh, actually I take that back on this one. This one, the coenzymes, I will tell you that you do need to memorize these. Let me see if I got a better table coming up. Yeah. I got a more simple table coming up. You do, and I'll explain how. That means you need to memorize the coenzymes and the type of reaction that they occur, that they use with their dietary precursors. So what I mean, for example, I will never call it biocytin. I don't hear people calling it biocytin. We all call it biotin. Okay, we talk about biotinylation and everything else. I guess technically it's called biocytin, but everybody calls it biotin. Biotin is in carboxyl transferases. So things that are going to be transferring CO, which CO gets transferred in vivo in the form from one thing to another as a carboxylate group. Whereas coenzyme A, which by the way it's also called CoAsh. Many times you may even see it abbreviated this way. For coenzyme A, it does acyl transfers or acetyl. Remember, acetyl, what does acet for acetyl mean? A-C-E-T? It's an old-fashioned term, but what does it mean? Like acetic acid, acetylation. It means what? Two. Acet. Formal, F-O-R-M-Y-L, not formal as in prom dress, but formal was the old one for one, and acet was for two. So acetyl groups literally means two carbon transfer. That's one of your functional words. Acyl is the generic one. It means it can be much larger. So this is used a lot of times for acetylation or acylation. So when we're talking about lipids, we will use coenzyme A. The next one, many times is abbreviated as cobalamin instead of saying 5'-deoxyadenosyl-cobalamin, which is coenzyme 12. Okay, and it's really cool. We'll talk about it at the next semester. It's very awesome. First of all, it's one of the ones that uses cobalt, and secondly, is it can transfer hydrogen atoms, not protons, the actual hydrogen in alkyl groups. It's one of the only ones you notice that does alkyl groups. It's really interesting. The next one, the flavins, that's FAD, FADH2, or FMN and FMNH2. That's lipoic acid, lipoic, whatever it's This is NAD plus or NADH. This is pyridoxal phosphate, which is pyridoxal phosphate. Well, we'll find out. It's also called pyridoxal whenever it transfers amino groups. That's tetrahydrofolate. Tetrahydrofolate is abbreviated H4. Okay, nitropholic acid. And then this is TPP for aldehydes, and that comes from thiamine. But I've got another table here that's from the old book that I don't know why it got, shifted up, but it did. Come down. Well, it got cut off, just the title for it. But it's the same thing in the sense that it has it listed out. All right. But yeah, those just help you because especially next semester, whenever we're talking about the types of reactions, say for example, when we're doing redox reactions, we're going to find out the difference between flavins and NADH, okay, which is the nicotinoids. But you can come to expect it. You'll say, okay, this is a redox reaction. Most likely, it's going to be utilizing one of these, either flavins or nicotinamide-based coenzymes. Or if you see a reaction and it says that it requires folic acid, then you're going to say, okay, most likely it's methyltransferase. Some type of methyltransferase that's occurring. All right. Some other terminology. Holo versus apo enzyme. Holo means it has everything required, all cofactors, all subunits, everything's coming together for catalysis. Apo literally means without. And it means it's usually lacking a coenzyme or cofactor for it to be fully active. Okay? So for RNase P, for example, the RNA was the apo enzyme, and it had that little protein in vivo for bacteria in order for it to be the holo enzyme. Sometimes we're talking about does not have whether or not the metal is present as a metallo enzyme. Sometimes this is a way to regulate enzymes, because you don't want enzymes unregulated and go willy-nilly, because then you die. And then there's prosthetic groups. These are usually covalently attached. However, once in a while they're not covalently attached, but they're KD, and we'll talk about KD later on. The dissociation constant is so tight that it's not going to come apart under physiological conditions. Okay, so one example for that one, which is not in our body, but is biotin with stripavimin. They bind so tight that you can't, even though it's not covalent, it might as well be. You can't get them apart. So, but usually when we're talking about prosthetic groups, one of the examples already, what's an example that we've already seen, a prosthetic group? I used that term prosthetic group that last chapter. What protein had a prosthetic group on it? It's not an enzyme, but it does have a prosthetic group. What protein would you use? Hemoglobin. Hemoglobin, and its prosthetic group is heme. The heme, the porphyrin meat. Righty. These are the enzyme commission, the EC, I think it's called enzyme commission. They give a number, like it's like a social security number, and it's the official unit. It's the official body that names enzymes. So it's like they have the ID tag that does, elements and stuff. The number always starts with either a 1 through a 6, and it may say something like 3 period, 2 period, 5 period, blah blah blah, and that tells you the class, the family class name, and then the subclass, and so on and so forth. Okay. So all enzymes have to fit one of these 6. Now that being said, what we'll find out next semester are these are the 6, and so they all will fit in that. But then there are some subclasses or common class names that supersede these. Like when we talk about, for example, dehydrogenase. And dehydrogenase is one type of oxidoreductase. Just like oxidases and reductases. There's dehydrogenase. That's probably the thing to do. Or kinases. We're going to find out kinases are involved. You can say are a type of transferase, a specific type of transferase. But so you're going to need to know your family, because if you know your family names, your enzyme classes and enzyme family names, that helps out a lot, especially next semester. So this semester, you're going to need to memorize at least these and what they do. Many of these make sense. Transferases, transfer groups. Okay. Oxidoreductases do redox reactions. I'm actually going to skip down to isomerases. Do isomerizations. Okay, so that means that within the same molecule or the same protein or whatever it is, they're going to transfer a functional group from one position to the other position, but it doesn't change the overall. Think back to organic chemistry and what an isomer is. It doesn't change the overall chemical formula. Okay, ligases are easy whenever. What's an example of a ligase? You ready? What? DNA ligase. Okay, DNA. Technically, there's more than one. It's a family. But and what they do, they literally, you probably in genetics. I don't know how simple it talks about it, but that's the one that seals the nicks. So that means it's like the Scotch tape. Like when I'm teaching to little kids, I'll say it's like the Scotch tape of the DNA. When you have DNA broken, the ligases stick it together. Literally though, it's formation of carbon-carbon, carbon-sulfur, carbon-hydrogen, carbon-hydrogen bonds. Utilizing a condensation reaction with DP or something. It's a mouthful. But, that's why we can see it's formation of these type of single bonds, condensation reaction with ATP, or usually some other type of NTP or ATP. Okay, we have done these two. Hydrolases are relatively easy. That's a hydrolysis reaction. Maybe more water is involved. And then a ligase. Ligases, whenever I was where you were at, that was the one that I always had problems remembering. A ligase, usually what we're doing is you're adding or taking groups off with the double bond involved somehow. So either you're forming a double bond or you're getting rid of a double bond by removing or adding other groups to it across that double bond. We don't see this one very often. 3 and 4, probably we don't see nearly as often. For us next semester, the middle of pathways we're talking about. Just because many times we're called something else or ligases, we just don't see a whole lot of them. And there is a reason why. We won't go into for this. Okay. All right. So. Yeah.
So ligases also break things apart then?
Yeah, they can. In theory. If it's an enzyme, in theory it can go forwards and backwards. We're going to find out, especially if we take enzymology, we'll talk about when the theory fails us, that kind of thing, All right, so this should be a review, just to give, we have any type of reaction that's going, and we are usually, with respect to enzyme reactions, we're almost always talking about things being reversible. Or even if they're irreversible, it just means that equilibrium favors one greatly over the other. So the free energy is equal to delta H minus T delta S. This is enthalpy, that's entropy. Don't forget the minus. Okay, remember this T it should be in Kelvin, because we can't have negative numbers in temperature. And that delta G not prime we went over the prime, I think, very first chapter or second chapter. Remember, that just means under biological conditions versus standard conditions is also equal to minus RT natural logs. That's a big thing of K, the equilibrium constant. So there's a way to link the equilibrium constant to all of this as well. Okay. So once again, this should all be a review. This is the reason why an enzyme or a catalyst in general doesn't affect the equilibrium constant. Because what is the equilibrium constant? If we were just going once again from A to B, we're keeping this as very simple as possible. reactant was A, and we're going to B, what would be the equilibrium constant? The equilibrium constant, KEQ, is equal to, what are big K's? How do you solve that? For chemical, remember this is the reaction. A. Pardon? KB? Not necessarily. I mean, I think you're making it even more difficult than what it is. I think you're now talking about kinetic rate constants. Let's say even more simple, like really, really simple. Whenever you're like trying to memorize this like gym chem, and you say K is equal to blank over blank. Product over reactants, right? And we're talking about concentration here, which would literally mean the concentration of B, concentration of A. Well, notice this is the uncatalyzed reaction going from A to B. You always have to add some energy into. Oh, whoops! Going from A to B, you always have to have some energy into it. It's called the activation energy. The top point's called the transition state. Remember, the transition state usually is given this little symbol as well. But when it's catalyzed, it just brings that down, whether it's an enzyme or something else, okay? But it doesn't change the amount of reactants or products that you started off with or you ended up with. And so that's the reason why it doesn't affect KEQ at all. It only affects this delta G. Now, this is definitely an oversimplification, because many times, in the simplest scheme, of course, this is the reaction coordinate, or time, or whatever you want to call it. And here, if we're talking about energy, you can either say E or G. It doesn't matter to me. I'm not a real stickler. And this is... Whoop! You can't go negative, but hopefully you get the idea. Here, let me see. Try to erase this last little bit. Okay. All right. So these are now, we're going to say these are our substrates, and this is our product. That's uncatalyzed. Well, now let's say we're going to catalyze this reaction. What's the very first thing that the enzyme is going to do to the substrate, usually? It's going to what?
Lower the activation.
Right, but I mean, what's the very first step that the enzyme would have to do here? Bind. Okay. So what's going to happen here is many times you'll see even written this way. Actually, I'm going to do it this way. It'll say E plus S. It's going to be reversible. Will bind to form ES, which is also called Michaelis complex. Just in case I say that, that's what I mean. And usually, I'm going to try to keep this relatively simple. It's going to form an EP, where the product is still covalently attached. This is assuming there's only one product. And then it's going to dissociate, because you got to get your enzyme back. Okay? So now we're going to walk it through this reaction coordinate. So we have E and S, it's the same, but now we're going to bind. You still have to add energy, by the way. And it's going to go down. So now, here's where ES is. No. Sorry. Okay. Then the chemistry is going to occur. It may be higher. One thing I want to point out, it may be a higher hump. It may be a lower hump. Okay? There are lots of different scenarios. That's why the book, I think, does it as an oversimplification. I'm going to do it this way. And so this little valley is where EP is. Whoops, EP. You have to add a little bit of energy and then down it goes. This is just one example. Now, once again, this and this doesn't have to be the same height. It could be that it takes a lot of energy to bind in the beginning. It could be that the chemistry step, this is called the chemistry step, where we're going to changing from substrate to product, could be take a lot of energy, or it could be the product dissociation right here takes a lot of energy. Because what's going to happen is it's going to take, when an enzyme is involved, it's going to go from being one hill, to a series of hills. Every step is going to have its own little hump, okay? And so you can count the number of valleys based off of how many intermediates there are. So we have 2 valleys because there are 2 intermediates. Now, if we wanted to, we can even figure out what the rate limiting step is for this reaction based off of which hill is the biggest hill. So if you're riding your bike, which hill, the first, the second, or the third one would be the biggest one to get up? The first. From substrate, in this instance, and so the way that we would say that is substrate binding is the rate limiting step in that mechanism now. That's not always true. Okay, sometimes it could be the chemistry step. It could be product dissociation, but then those hills will be bigger. Just like I want to point out, the way I have it drawn, ES and EP in this instance are both at the same minimum, like they're at the same level. That's not necessarily true either. It just so happens to be that way. So we'll work through some examples later. Okay? And so that's where I want to stop off for today's lecture.